closure.
An example of risk analysis. We will do a numerical analysis. Numerical analysis of risk. That's a numerical analysis of risk. Yesterday I asked a question and left at I went blank. And the question was whether this is analysis of risk regarding in the metro, automatic door closing is there in every coach. Unless the door is closed, the train won't start. Has this been done? Any example has been done on this by Mr. Irfan?
No.
It was not done.
No.
Okay, so let's do that. So this is to demonstrate. Yesterday I told you the block diagrams. Is it not? Calculate the risk. Is the risk acceptable? Yes, no. Then if it is no, go for a risk reduction. If it is yes, close the problem. This diagram yesterday I drew. You get that?
Yes, sir.
That is something like this. There is risk. You calculate. Then you make a decision. Acceptable or not. If it is not acceptable, how do I reduce the risk? You think of how to reduce the risk. Go back to the old problem. If it is yes, then close. You're done with it. Now, how do I do yes? Yes, I do, because I must have a risk criteria. Risk acceptance criteria. If I know a door closing, for example, 100 years, if is my risk acceptance criteria, I calculate the risk. Is it is 1 death by 100 years? Yes, I close the case. If it is 2 deaths by 100 years, it is no. Then I go back and look at how best I can further reduce the risk. This is what the thing will. Hello, Vinay, are you there?
Yes, sir.
Because the risk seems to be a high risk topic here. Because every time I wonder whether we are getting. Okay, let us do this example quickly. So this is just to demonstrate that loop. Calculate the risk, find out acceptable or not, then go back and do what? This is what it is. Let us take a hypothetical case. Here the hazard, passenger trapped in door at departure. First question, why do we say it is a hazard? The fellow is already trapped. Hazard is an accident waiting to happen. That's what we said. Hazard is an accident waiting to happen. So a passenger is already trapped in the door. Is it already an accident, or it is already an accident waiting to happen?
Waiting to happen.
Waiting to happen.
Yes.
Good. Why? Because the accident will now happen if the train starts moving. If the train starts moving, the accident is definite for sure. So with this, a passenger getting trapped in the door is a hazard. This is the hazard we are looking at. This is analysis we are going to take. Good. Sorry. So let us take the facts now. First, the number of trains in the fleet. How many trains do we operate? Let us take 80 trains. These are well, for any situation. You must know what are the facts. What is that we do? Then B. Departure per day per train. There are many departures. The train departs station A, stops, departs at B, then departs again at station B, goes to C, stops, again departs. So that is why he said departure per day per train. You may be wondering how so many departures per train can be. Let's say 100 departures in a day. Then it comes back, starts again. So 100 departures per day. These are the figures, easy calculation. So the number of departures we can calculate. Number of departures per year will be 365 into A into B. This will be equal to, what is this? Something like this. You can verify, otherwise you can correct it. Doesn't matter. This is the total number of departures. These are things which I have to take from the system of operation. This information I have to take from the system of operation. Now, what are the human action barriers? Suppose a hazard is trapped in the door. There will be some barrier. System has to have some barriers, something to prevent that. Now, first, the human aspect. Let us assume that is the passenger is trapped in door once per departure. At least one passenger, let's assume, we start with presumption. One passenger at least gets trapped in every departure. And also assume the train driver, you know what the driver is supposed to do? The driver is supposed to look through his, either there will be a TV screen in front of him on the platform, not in the train, on the platform in front of him. So he looks at the platform TV screen, he can see the entire train back, where all the doors are closed, where anybody is struggling to get in, or anybody is struggling, anybody is waving. So he will see all those things. And if something happens like that, if he observes, he doesn't start the train. This is the first input he gets. This is the first check that you prevent an accident, because the driver is supposed to observe all the doors at the before departure. He doesn't get down and check. He sees through a TV screen, which you will normally find on the platform, just in front of him. You can look at the screen, you can see all the situation back of the train. Now the train driver fails to, so far this to happen, the fellow should have failed. Otherwise, he won't start. Fails to check doors. this with the taken into account. This is the probability of this. You know the examples. So let's say 2 power 5 into 10 power minus 3. I have given the reason also. How did we get this figure? Why should we assume this 2 power 5? Why not something else? A reasonable assumption is driver misses check 1 in every 4th day due to lack of concentration. Not every day he misses that. 1 in every 4th day. That means this is equal to 1 by 4 B. B is what? Departure. This. I have given you B here. B. 1 by 4 times B is this. Is this factor. So you have been taught fault tree analysis, is it not?
Yes, sir.
Yeah. Now you note down these things. I am going to just go to this thing. So now how does this look like? Now I have an input here. There is a passenger is trapped. What is the probability? This is 1. What is the probability of this driver fails? Driver fails. To notice this, I am taking it as 2.5 into 10 power minus 3. This is an AND gate. If both of this happens, the passenger is trapped and the driver fails to notice, definitely it is a dangerous situation. And this probability is, this I said is D, this I said is E, so it is D into E because it is an AND gate equal to 2.5 into 10 power minus 3. This is one input. Is this the only barrier we have got? In the train there are many barriers. There are technological barriers. What are they? There is a trap detection is there. If the door doesn't close, the traction, the traction motors won't start. There is an interlock. It detects the sensing of the doors. If it fails to sense, it won't start even if the driver wants to start. So there is technical barriers. Human barrier is the driver. First, he has failed. Second human barrier is the individual passenger himself. Nobody would like to get trapped in that. Somehow he gets trapped. We take that as every trip there is one fellow gets trapped. So this barrier we have calculated. This is the probability of this thing going to happen. Now let us see the technical barriers. Some more failures have to happen if an accident has to happen. Remember always in railways, and so also in many other systems, an accident does not happen just by one mistake. At least 3-4 mistakes have to happen. Then only an accident happens. They say in an aircraft, if not one mistake, the failure happens. If 16 mistakes happen, 16 mistakes happen one after the other, one after the other, one after the other, and then only there is a failure and there is going to be a crash. That is the kind of design they do for that. So also in the railways, one mistake, nothing happens, whether it is surface rail or metro. There have to be 4 or 5 mistakes, one after the other have to happen. Unfortunately, when an accident happens. So the technical barriers are, one is the next factor is traction block. Traction block. That means it detects the door. When the door is open, it will start fully closed. It won't start. This probability is by past data, FRACAS, failure data analysis. People record data keep it in the thing. How many times it happened? The driver comes and gives information. Okay, so many times it didn't start because of the door did not close. So from the database, you find out the probability is 1 into 10 power minus times per departure. So this is one failure should occur here. The second technical barrier is the trap function itself fails. Trap function is the one which detects whether the door is fully closed or not. The trap function fails. The trap detection function rather fails means it fails. Meaning what? Erroneous declaration of door closed. It says wrongly door is closed. Though somebody is trapped inside, but it gives a command door is closed. It's a malfunction. Now this we take a probability of 1 in 10 power minus 4. This again is from the data, from the past history of the thing, how many times it fails, how many trips, all from the data you can get it. So there is a failure here, Now this will be what gate for the accident to happen? This will be an AND gate or OR gate?
OR gate.
Excellent. So it will be a OR gate. Either this or this happens, then it's going. So this will be, this is F, this is G, sorry, this is G. So this will be F plus G will be the output. So if the accident has to happen, these two phenomena has to happen, what gate it will be?
OR gate.
The barrier has failed. The human actions also have failed.
OR gate, sir.
Huh?
OR gate.
OR gate or AND gate? I say it is an AND gate. Why? Man has to be struck, the driver has to fail, and the truck, this also, one of these has to fail. Unless these both conditions simultaneously happen, there won't be an accident. If this is not true, this input won't be there. If this is not true, this input won't be there. You need both the inputs, this to become true. Okay? So, the accident here now will be C per year will be, I will tell you, C into what I have written here, to D into E into F plus G. You have got D here, you have got E here, you have got F, you have got G. Why have I put G? Because I wanted to find out per year. This is so many times this will happen per year, because when I wrote C, number of departures per year is 3 into 10 power minus 6 per year. These are all per departures. All these inputs D, E, F, G are per departures, and so per departure in the number of departures per year will be so many things will occur. So this if you put all the numericals there, it comes to almost 1 per year. 1 per year. That means one person will get into a serious injury every year. This thing. Now we have come to the point. Now we have to decide, is this acceptable? The next question is, in the block diagram, I read, take a decision whether it is acceptable or not. Now this is something which we have to decide. This nobody else will decide for you. The administration, the operator, the designer, everybody has to sit together and say that yes, is this one person getting injured, can be one death per year, is it acceptable to you or not? Obviously, the operator or the administration will say, no, sorry, this is not acceptable to us. But you have to write in the, this is one of the inputs in the safety management system, which Mr. Sudhir Kumar must have taught you. In the safety management system, you have to do the analysis. Mind you, this is only one hazard. This is only one hazard. There will be so many hazards, so many subsystems are there. For each hazard, you have to do an analysis like this, and then you have to write, this is say 1 per year. Something else happens, this is 1 per year. Collision happens, this is 1 per 10 years. If something else, train parts, it is 1 per say 100 years. Like that, you have to do a hazard analysis and write in the safety management system. Once you write that and submit, then somebody has to decide whether these are all acceptable to you or not. You have done as a consultant your job. But somebody has to decide whether it is acceptable or not. And you also may have to say, look, this so-and-so metro we have designed, it is not acceptable. They follow a different criteria. So, now the decision, acceptable or not. Obviously, it is not acceptable. So the administration, let's say it says, the hazard leading to an accident like this, we will accept is 1 in say 10,000 years. So when you come back to that loop, you remember that loop? So I have made the decision. Now I have to make, is it acceptable or not? Or not? If it is not, then go look for reducing the hazards. Reduce hazards and go back. So we have taken this loop because no S. S is not there. Because our criteria doesn't fulfill. So we don't take this loop. We take this loop, go and look for reduction hazards. Now let's see, how do we, is it possible to achieve this at all or not, and if so, let's look at some theoretical way how to do it. The first thing, analysis of the situation. As an engineer, what you will do, this detection failure, can I do something to reduce it? This seems to be a little high. How do I do a detection failure? Normally, when the detection fails, can anybody guess? The door wide opens and it closes. The probability of the detection failing is when the door is wide open, and the door is in the middle, the door is say 10 centimeters away, 5 centimeters away, 2 centimeters away, 1 centimeter away, 1 millimeter away. Where do you think the chance of failure will be? A wrong detection happening will be at what gap? Where the probability will be high?
Yes. No, where will it be high? At what distance? The smallest distance.
We will ask ourselves a question, looking at the things, which are the factors we can improve. So we'll say, I want to improve the detection failure. Okay, somebody says, I will. The answer is, the question is, why do you want it? Already we have taken from the data. Why do you think we should improve the detection failure? Then another colleague says, let us look at what is the probability of the detector failing. Is it at a small distance or it is more, is it a small gap or a big gap? Hello.
When will it have the at the smallest
Chances
gap?
of failure are
The smallest
up
gap.
to-
Sir, at the smallest gap.
it's a limit switch. The detection failure is nothing but a limit switch. There is a switch that when the door comes closer and closer and closer, the switch touches each other, and then it says, "Okay, door is closed."
Yeah.
That's all. There's no magic in that.
Yeah.
It's kind of a limit switch. There are two switches, one in this door, one contact in the door A, one contact in the door B. They come closer, and when they touch each other, the system says, "Yes, door is closed." Now, what is the chance of this failing when the door is wide open, middle open, or it is a small gap? Where the chance is more?
Okay. Wait a second. See. No, when the system will fail. When will it? When will that thing fail?
The wrong indication. When will the wrong indication? What I mean is, when the wrong indication will come that the door is closed.
I think the
Door is
smallest
still
gap,
open.
sir.
Wrong,
It is
wrong
almost.
indication will come. The door is somewhere in the middle. The chance of wrong indication is more, or the door is almost closed. There's a small gap. Then there is a wrong indication chance.
Almost closed.
But if the passenger is
If it is wide open, the contacts are too far away. The probability of saying that these two are touching is very less.
yeah,
Is it not?
yeah.
When it comes closer and closer,
The
somebody
chance-
can adjust the switch at 1 centimeter gap.
Yeah.
Somebody can adjust the switch at 2 centimeter gap.
Yeah.
Somebody can adjust the switch at maybe 3 centimeter gap. Nobody will adjust the switch. And they have to, if you say 4 feet away, you can't adjust the switch. They come and touch. Is it not?
Yes.
So as the door comes closer, you have to be very careful in the switch adjustment. So one of the Berlin guy said, "Look, let us look at this. Why the limit switch? There is some problem in the way in which sorry. So only when the gap is small, the wrong detection will come. That yes, door is closed, even though there is a gap. A small gap can be produced how? Not by the man getting stuck or woman getting stuck in between the doors, because that gap will be big. It will be at least 1 foot away, whichever way. Even the sideways, if you get stuck also,
Minimum
it
1
will be
foot.
at least 6 inches away. So small gap means
Mechanical installation.
what? Your finger can be stuck. A child's small arm can be stuck. An umbrella's rod can be stuck. These are all small possibilities where a wrong detection can come. Is it not?
Yes.
Not the human body, full body, if it is stuck in the detection switch, definitely will say, sorry, the door is not closed. There is a small object like your finger is stuck. It's a small thing. But still it will cause, if the train starts, an injury will happen.
Yes.
Because you may be standing outside, you may not be inside. Your finger, if you are inside, the finger will get crushed. If you are outside, your finger will be dragged and something will happen to you. So in any case, it is likely to be an accident. So only small objects, when it gets stuck, the detection, there is a chance of failure. So this brilliant engineer said, okay, let us not set the limit switch like this. Let us adjust the limit switch detection failure only for small objects. Big objects, definitely in any case it will indicate. Is it the thin objects? Assume it occurs 3 times per day. That is D equal to 3 by P. A, B I have indicated already later. Now you adjust the sensors. Adjust sensors so that the failure rate, that is a wrong detection, wrong side failure, becomes 1 in 100,000. The previous one was different, now it is different. 1 in 10,000 departures. I adjust this. What else can I do? Because there is no unique answers for all those things. This is a brainstorming session everybody has to do. Everybody has to take part, come with ideas, funny ideas, think out of the box. You will get some solution. So another engineer suggests, let us improve the human failure side. So how do we do that? The driver has failed to. Now, you cannot help, you can only tell passengers, please be careful, don't keep anything inside, fully get inside, otherwise don't get inside. All these advertisement you can do. The driver will definitely fail in every fourth trip. We said he is a distraction, he doesn't observe. So nothing you can do about it. So another engineer suggested, it's a hypothetical case. He said, why not we put the guard, the guard is in the rear of the train. We tell the guard, he walks through the train when the train travels from A to B, comes to the driver end, he gets down, then walks back towards his coach at the end. While walks back, he checks whether all the doors are closed, anybody is stuck, anybody is making noise, anybody is struggling to get out, anybody is this thing, he checks all the doors, then goes back into the rear coach, then tells, okay, let us start the train. Definitely it involves manpower. Maybe even the dwell time has to increase a little bit. The dwell time meaning the train stopping at the station has to increase more little bit because the fellow has to walk back all the way. Suppose you have a check like this, then definitely we can improve the chance. If I do this, then he said the failure, one failure will occur per 10,000 departures. You can drastically. Hello, are you on the line?
Yes, sir.
Okay. So if I read out the diagram now, the first AND gate, we said one person gets stuck. Now we are saying only the thin objects will get stuck. So it will be 2 into 10 power minus 2, 3 by b, d equal to 3 by b, this factor, 3 into 10 power minus 2. The procedural improvement by the guard walking back all the way, we reduce this to 1 10 power minus 4. This is an AND gate. So this becomes 3 into 10 power minus 6. The other parameters, there is an OR gate. We said the traction block, no change. So that remains as 10 power minus 6. Sensor I have adjusted. 1 into 10 power minus 5. This is an OR. This both becomes input to the next AND gate. So this comes to from 9.6 into 10 to the power of minus times per year. So this we have reached a figure of 1 instead of 1 per year. We reached a figure of 9.6 10 power minus 5 per year. Is very acceptable. So that means nice to take it as 10, 9.6, 10. So 10 into 10 power minus 4. That means 1 in 10,000 years. One accident will happen and the door closing case in 10,000 years you achieved. Now there's a different matter altogether whether these two assumptions what I have made is workable, practicable or not. So that has to be in the brainstorming, people will decide. Oh, this is not workable, we'll rule it out. Yeah, this is a brilliant idea. It is workable, let us do this. So there may be many solutions like this which comes in loop closing. Just go around and round and round. Find suggest variation solutions, then probabilities, put it in the FTA and find out what is the accident rate. Finally decide acceptable or not acceptable. So this is only a numerical example which is highly theoretical to demonstrate how the whole system, how the whole team has worked to solve the problem which is not acceptable in the hazard analysis. And there will be thousands of hazards like this in a metro system. It won't be one or two. So each hazard, some hazards initially you can know it's not going to cause an accident. At the most, it will cause a detention of the train. So I don't worry about it because now I'm talking about safety. Some hazards like this, many will say no impact on safety, no impact on safety, no impact on safety. Then one will say, yeah, it will have safety impact. Then you look for targets, look for other metros targets, and then see how improvements can be made. So like that, you have to close all the thousands of hazards that in the safety management system report, you have to see what is the original, what is the mitigation measure you are suggesting, and what is the final, which is acceptable to the administration. This is the job, this is in nutshell what you do in the safety management report or safety management system. It's a very involved, time consuming, lot of people have to be there, the signaling expert has to be there, rolling stock expert has to be there, operational man has to be there, depot maintenance man has to be there. Everybody has to sit and do it. It's not a one man's job.
So this has to be done at the design stage only.
Yeah, it's a design stage.
So it ideally has to be done by the owner's consultant.
No, the ISA when he is verifying, the first the supplier who is doing this, like in this case, Thales or the rolling stock supplier, because this is a door closing.
Yeah.
Door closing is Thales.
Rotem.
Who is supplying the Rotem, sorry. The Rotem fellow has to do all this exercise and submit
But
to
sir,
L&T.
But when they are deciding the from which vendor to procure, won't they give it in?
No. You only specify in your target.
Okay, but to set the target also, they will have to do this exercise.
So what we do, that is what is going to be. My next lesson is on that.
Okay.
How do we specify targets in the tender? After all, you have to tell that fellow, is it not?
Yeah, we have to tell the vendor that.
Vendor. We are floating a tender, asking for things. So we have to tell him what is the target, what is the safety target.
Right.
So like the RAMs. So my next topic is, now I have completed the safety portion. So we talked about SIL was the only thing I wanted to touch upon, which I have completed. So I thought I will just provoke, and I'm happy that you have been provoked. I wanted to provoke who will do this, who will suggest this. The L&T Hyderabad Metro, when it floats a tender, he has to get targets. So all the RAMS parameters, RAMS, for all parameters, you have to set the target. What is that you want? Then only the manufacturer will start working, because he has to take a decision. The decision loop is there. Is it acceptable? So the criteria, you have to mention the criteria. So the next, do you have time now to start?
Maybe another 10 minutes. So you can just introduce the thing and then we'll continue.
Yeah. So next I'm talking is, now I've closed RAMS, everything is closed now. If some special interest is there, when I come back, which I hope to come soon, we will start face to face, we'll have discussions. There are some things which I left, which I said we have to do on a face to face interaction, those things we will do. Now the big question is, this all of you have to participate, because I am proposing a paper in the Applied Symposium Conference, which has been accepted, and my target date is 10th of June. I have to submit, and which is to be presented in Chennai and the International Applied Reliability Symposium in somewhere in August. So my topic was how to specify the RAMS parameters for a metro project. It's very easy to make a small problem and say the lambda is so much, calculate reliability at 100 hours. Something else, two things are working in parallel. What is the reliability overall? What is the unavailability? All those things. These are all easy matters. When it comes to application, is the problem. The problem is, I said, how do you specify for RAMs for a railway system? Let us take a metro. Or what is that operator should specify? S is a separate matter. You take out S for the time being. Let us take RAM. How do I specify RAM is the question. So I want you people to think about it, but I'll just give clues. Do we specify all the subsystems? There are two methods. Either I do what is the overall I want. Overall, what is that I want? Or I can specify individual subsystems. Individual subsystem. I do on this approach, or should I do this approach? Is the question. Or I do a combination of these two. So overall, when I say, we have seen a problem also. What is the overall parameter we said in Hyderabad Metro to specify?
Punctuality.
Punctuality.
So, punctuality. This is what Hyderabad Metro, the government has given to L&T. I want 99%, let's say. This was to L&T. L&T has to draw a specification subsystem wise, wrote the call for bids from various people. How will they do that? They also will say 99%, leave it like that. Yes, one option. Or will they give individual? You all have access to the rolling stock specification?
Yes, sir. Not
They have
all of
access?
them, but the electrical and mechanical group.
Yeah,
You
okay.
guys don't have it.
Okay.
Yeah.
And so kindly go through that specification once. See whether any reliability, that is the system performance requirements are given or not. And if so, what is that they have mentioned in that? RAM parameter, then there will be a chapter on RAM. What is that they have specified? And if they have specified, then that's what we are going to see. If that specification will meet, will it contribute to 99% of reliability or not? Is the question. And it should not contradict. They are very complicated issues. So now you said punctuality. I have used the word reliability, availability, and maintainability. Punctuality. Punctuality. Is punctuality is equivalent to what? Is it equivalent to reliability? Is it equal to availability? Definitely it is not maintainability, but which of these two is punctuality in the case of a train?
Availability.
You are saying availability, right?
Yes,
Now,
sir.
what is the definition of reliability?
Probably.
Whether a thing works for an interval 0 to t. Is it not?
Yes.
Without failure, it has to work on an interval 0 to t. And availability is the probability of its working at any instant t. The reliability is for an interval, availability is for an instant. Which is more appropriate in the case of punctuality? The train starts at station B at t equal to 0, arrives at station B at t equal to t. So 0 to t is an interval.
Punctuality
So which
is for a
so it has to reach at the correct time at t. That means which is more reliable to punctuality?
availability.
Which is more related to punctuality?
Availability, sir.
Availability is for
Punctuality is
whether
at,
the train
for,
is working at a particular instant or not.
yes, sir.
Reliability is
For a
without
period of
failure,
time.
it should travel from 0 to t.
Yeah.
That means the train should run without a failure from 0 to t. Then only it can reach the station B at correct time.
Yes.
So I am saying reliability is punctuality. Because 0 to t, there should not be any failure. If there is a failure, the train stops and you lose your target time of reaching there. The mission time is, I am saying for a train, the mission time is from station A to B. And reliability is always related to the mission time. So I am saying the reliability is more akin to punctuality.
So if the train has to be at a particular station at the designated time.
Yes,
So it is,
at the designated time. But in between what happens? To reach the designated time, it has to travel some distance before that without failure.
okay.
Is it not?
Right,
To reach a
right.
station at the
Right.
designated time,
Yeah.
it has to travel other than the starting point.
Yes.
Is it not?
Yes, sir.
But at the starting point, if I start late, then also I get fired. Is it not?
Yes.
Now the question is, at the starting point, what is important? If the train has to come to the platform in time, it doesn't have to try, it has to only come from the depot.
Depot, yeah.
But there, the train should be available. It should be in workable condition
At the depot.
at the depot. If it is not available there, it cannot come to the starting point.
Yeah.
And if I start 5 minutes late, then my punctuality is fired everywhere. And afterwards, I may have 100% reliability at every station, but I still lose 5 minutes at arrival point.
Okay. So punctuality
So
is
the another way of looking at it, availability is punctuality. So this question has been going on for, I think, 30-40 years. People still no conclusion. What is punctuality? Whether it is reliability or it is availability, or it is both, or it is a combination, nobody knows even today. But they all know that the reliability and availability is related to punctuality. In what way they are related, there is no final answer. But we know intrinsically that feeling that yes, if more reliable, more punctual, more available, more punctual. Yes. But how do I relate these two? No idea. So you people think about it. How do we approach this? And what I am presenting on behalf of IMRT, that is on behalf of all of you. So you can also search in the internet. You can give me inputs. So if it is something valid is there, I will definitely include and acknowledge your inputs that yes, you have contributed something to this paper. It's quite, I have not come to any conclusion yet, what is related. I am searching. I'm not able to everybody. Some people say reliability, some people say availability, some people say no definition is available. So how do we meet this criteria? Okay. So tomorrow our discussion is going to be what is punctuality and how is it related to RAM. Then search, we'll discuss. Okay.
okay, sir.
Right. then I'm signing off. Huh?
Okay, sir. Fine.